So towards the end of the last video, we were talking about derivation of equation of motion for the free vibration. So in this case, there is no damping involved, or there is no forced vibration oscillation, force function on the on the mass. And I've drawn the diagram neatly again here for our understanding that there is a stretch position, and due to the weight of the uh, mass, the spring reaches a equilibrium position that is called the static equilibrium position. And then now our problem is to consider the deflection above and below the static equilibrium position. So we have taken this direction as positive, the downward direction is positive, and at a static equilibrium position the forces are balanced, mg and k theta are balanced, and when a displacement x is applied, initial disturbance, then the forces change. Downward force is still mg, but the upward force becomes k delta plus x. So if you see forces in the downward direction, you will see mx double dash. The forces in the net force in downward direction is mg minus k delta plus x. So k delta plus is towards top, so minus. Simplify this equation, you'll get the equation for free vibration. So this is the equation for free vibration. Mx double dash plus kx equal to 0. This equation can be rearranged to be written in this way: x double dash plus k by mx is equal to 0. So if you compare this equation with a homogeneous second order linear differential equation, second order linear, because we will not go into solving the equation exactly, we will just derive the solution from, because it's a generic form of a linear equation: x double dash plus omega square x is equal to 0. So this is a homogeneous second order linear equation. Homogeneous means because there is no forcing term here, so it comes coming as 0. And second order means x double dash is involved. So we already know the solution for this problem. So we compare our equation of motion with the standard homogeneous second order linear equation. We will get that if we have omega square as equal to k by m, or omega as equal to square root of k by m, then our equation is pretty much same as the homogeneous second order linear equation. So the solution for second order linear equation, homogeneous linear equation, is known, is pretty standard, and this you can refer from any mathematics textbook. The solution is x is equal to a cos omega t plus b sin omega t. You can quickly verify whether the solution is correct or not. So if you take a derivative of x, dx by dt, you will get cos theta. Derivative of cos theta is minus sin theta minus sin omega t multiplied by derivative of omega t, that is omega, plus b cos omega t. Derivative of sin is cos, and the derivative of omega t will be omega. And then if you take second derivative of this function, so derivative of d by dx of above, d by dx of dx by dt, sorry, d by dt of dx by dt, then you will get differentiation of the above is a, and differentiation of sin omega t is cos omega t, and then again differentiation of omega is omega. So there is already one omega, there is a negative sign also, you get one more omega here, plus b omega, derivative of cos omega t is minus sin omega t, and then you will get derivative of omega t is equal to omega. So if you rearrange this equation, you take minus omega square outside, you get minus omega square whole bracket of a cos omega t plus b sin omega t. This, if you compare with your original equation, that a cos omega t plus b sin omega t is equal to x anyway. So you get minus omega square x, and d square x by dt square is x double dash. So ultimately you have got x double dash is equal to minus omega square x, or x double dash plus omega square x equal to 0. So you have got back your second order linear equation. So this is a general solution for that. Also in the solution, if you take a cos omega t as a solution, that is also valid. But since you have two initial conditions, that is the initial velocity and initial differentiation, so you should have two unknown parameters. So this equation is having two unknown parameters. So that is a and b. These two are unknown constant that has to be determined by the initial condition. Determined by initial conditions. So in our problem, we have basically two initial conditions. Since there is this mass m is displaced x from the equilibrium position, so and at any instant it will have some velocity x dash. So we know at time t is equal to 0, we will have initial displacement x0. Let's say x at time 0 is initial displacement, and at time t is equal to 0 will have a initial velocity x dash 0. And the third quantity is the acceleration. We cannot have a separate quantity for acceleration, because in this system acceleration is proportional to x, that x dash is equal to minus omega square x. So hence if x is known, x double dash is known, so we cannot have a separate initial condition for x double dash. We can have only two initial conditions. One is x at time equal to 0, and one other is x dash at time equal to 0. So these two initial conditions, and we have two unknowns, two unknown constants. So we have a closure here. We have same number of known constants. That's why we have taken an equation of form a cos omega t plus b sin omega t, because just a cos omega t can also serve a purpose. It is also one of the solution of this equation, x double dash plus omega square x. So a cos omega t or just b sin omega t is also a solution of the second order linear differential equation. But since two initial conditions are there, we have taken two unknowns, so to make our solution general. Now to get the unknowns, what we can do is that we know the equation a cos omega t plus b cos omega t. Now here put t is equal to 0, and you will get x is equal to x0, the initial displacement of the system. This just means that you are starting your analysis not from the 0 position. You are starting your analysis from some time when displacement is there. So you are making a general solution is present. You are not constrained to start your solution from the equilibrium position. You have at a particular instance, you know that the time is 0. From here you are starting your observation, and some displacement has already taken place. So these are initial conditions for you. Initial conditions. Initial condition need not to be 0 conditions, like equilibrium conditions. Just to make a solution general, we are using all these derivations. So if at time equal to 0, x equal to x0, that will be equal to a cos 0. Cos 0 is 1, plus cos omega t plus b sin omega t, and b into 0, sin 0 is 0. So a you will get equal to x0. Now for determining b, you know that x dash 0 you know. So the expression for velocity was minus a omega cos 0, because t is equal to 0, plus b omega, sorry, this is sine sine 0 and b omega cos 0. So sine 0 is equal to 0. So you will get b as cos 0 is equal to 1. B as x dash 0 divided by omega. So now if you substitute the values of a and b in our final equation, that is a of cos omega t plus b sin omega t, you will get the final solution as that x equal to x0 cos omega t plus x dash 0 divided by omega sin omega t, where omega is equal to square root of k by m. So this is your solution for free vibration. So with this solution, if you know the any time instant t, you have to know the initial condition of the system x0 at s0, and you can get the displacement, velocity and acceleration at any point of time. And the term omega, that is equal to k by m, is called the natural frequency of the system. Natural frequency of the system. So actually this is the angular frequency, and to calculate the natural frequency in real domain, we will see the equation here. The displacement equation are consisting of terms cos omega t and sine omega t. Now we know that the cosine and sine function is having a period of 2 pi. So this is pi. Similarly, cosine function also is having a period of 2 pi. So these functions are having a time, these functions will repeat themselves after a period of 2 pi. Hence, if time period of oscillation is t, capital T, then from time t is equal to 0 to time is equal to t, one cycle will be completed. So our omega t, the quantity inside the bracket for the cos or sine function, will be equal to 2 pi at time is equal to t. So hence omega into capital T will be equal to 2 pi, or we will get that omega is equal to 2 pi by t. So since t is a time period, then f, the frequency, is equal to 1 by t. So this is equal to 2 pi f. So from this relations between the angular frequency, time period and the real frequency, we can get the actual value of the time period and the real frequency, because we know the value of omega from our derivation. Omega is equal to root over k by m. K is a spring constant. So the time period is 2 pi by omega. So time period will be equal to 2 pi m by k, and the frequency will be 1 by 2 pi k by m. So like this you can find the natural frequency of the system. The determination of natural frequency of the system is of the main interest in many applications, because when a system, any system, whether a spring mass or a cantilever beam or a torsional pendulum, any component, even complicated industrial components like say gears or belt drive, shafts, cam, axles, any component, all mechanical components which are non-rigid, which are having a capability of vibration, which are non-rigid and elastic. So when they are deformed from their initial state, they try to come back to their original state. So that means when deformed, they try to come back to initial state. All such components are capable of vibration. So this will include mostly all the metallic part, because metal is an elastic element. When you stretch it, it goes to a deformed state, and when you release it back, it comes back to its original position. While coming back to its original position, it overshoots and it reaches the other extreme, and hence a vibration is set up. So vibration is set up in all mechanical components. You have vibration setup possibility. The degree depends on the stiffness of the material, that is K, and the characteristic mass of the material. So natural vibration occurs. So the frequency of natural vibration is very important. Frequency of natural vibration is very important to determine resonance. So from here you can get an idea of what is resonance. So when a system is deformed from its natural state, it will resonate at its natural frequency. So if in a system you are forcing at natural frequency, that means you are supplying the energy at natural frequency, then the amplitude of oscillation will grow, and sometimes the amplitude of oscillation can go up to infinity also. So in such cases, the amplitude can be detrimental, can cause serious damage to the material, and it can even cause the material part to break. So such conditions where the forcing frequency is equal to natural frequency are called resonance. So in most of the cases in mechanical failure in the history of engineering, it is seen that the failure doesn't occur because of the design of the component, but sometimes when the system is subjected to an external forcing. So the external forcing excites the system at the natural frequency, the amplitude of oscillation goes to very serious limits, and the component fails. Even with very small loads, the component can fail. With small forcing, the amplitude can grow very high and the failure can happen. So that is why it is very important to find out the natural frequency of systems, and then you make sure that the system is not, during its operation, wherever it is applied, the system is not subjected to a forcing, a periodic displacement, the frequency of which is same as the natural frequency. So to make sure that calculation of natural frequency is important. Frequency important to avoid resonance. So as you can see from the formula for natural frequency is pretty much straightforward. You don't need any differential equation for that. You just have to know the stiffness of the system. K is stiffness. In this derivation, it was the stiffness of the spring. In a general case of mechanical component, there will be some characteristic stiffness of the system, the tendency with which it wants to come back to the initial state, and m is the mass or inertia of the system. So ratio of stiffness to inertia, square root of that will directly give you the natural frequency. So I'll write that statement, the observation here, and this you must understand, and you should grasp this concept very carefully, that the undamped natural frequency, the natural frequency system, does not depend on the initial conditions, initial displacement, initial velocities, or amplitude of vibration. It is a natural property of the system. It only depends on mass and stiffness. So since the mass and stiffness are an inherent property of a system, inherent property of a material, so it only depends on that. So the natural frequency is something which is inherent to a system, and it doesn't depend how the forcing is applied, how the oscillations are occurring, whether there is a damping or not. Doesn't depend on any of that. The natural frequency will remain characteristic to a system. So apart from the force balance method that we just saw for determining the equation of motion of the mass, that we calculated the unbalanced forces, that is equal to kx, and we equated it with the acceleration minus kx equal to mx double dash. So like that we found the equation of motion of free vibration of the body. Apart from this method, there is like you can also find out the equation of motion by conservation of energy. So this is also one method to find out the equation of motion, and it is helpful in many cases where the geometry is complex and force balance, doing a force balance is typically not possible. Then this method of using conservation of energy for determining the equation of motion comes in very handy. So I'll just demonstrate this method for our same problem of spring mass system, and then the same principles apply for any different type of configuration. Now we have seen questions coming in GATE where some typical oscillatory system is given, and then in those cases it is much easier to solve the problem by using the energy conservation method than by doing the force balance. So in the present system, at any, like if this is the zero position, this is the static given position. At any position, if the deflection of mass is x and the velocity is x dash, the acceleration is x double dash, then downward direction being taken as positive. So the kinetic energy of the mass will be equal to half mv square. So in this case, half mass into x dash square. X dash is velocity and x double dash is acceleration. And what is the P of the system? Potential energy of the system. Potential energy of the system is stored in the spring. So the spring is where the potential energy gets stored, which tries to bring the mass back to its original state. And the potential and the energy stored in spring, as you can remember from your theory of materials classes, it is equal to half kx square, where x is the extension in the spring. So extension in the spring. So since the static deflection is also there from the zero position, there is a delta static deflection also. So net potential energy of the system will be half k x square plus half k delta square, but we will neglect that portion of the static deflection, because that energy, that potential energy will be always there, and we are only considering the dynamic, the potential energy and the kinetic energy which are changing with time. So we know that the dynamic potential energy plus the dynamic kinetic energy, the summation of these two energies is the total energy of the system, and it remains constant with time for free vibration. So let's say this constant is some value k, and potential energy half k x square, kinetic energy half m x dash square. So this is the equation for conservation of energy. Now if you differentiate both sides, you know that differentiate with respect to x here, not with respect to time, just the x here, because this is a identity and we can differentiate it with whatever quantity we wish. So half mx double square, so to dk by dt. So k is a constant So d by dt of this expression, the total energy is equal to 0, because dk by dt is equal to 0, derivative of the constant is 0. Now we will solve this problem, take the differentiation. This will come as half k into 2x multiplied by dx by dt plus half m multiplied by 2x dash dx dash by dt equal to 0. Now 2 and 2 will cancel out, so we will get here kx x dash dx by dt is nothing but the velocity of the mass, and that is equal to x dash plus m x dash, and the differentiation of x dash is x double dash, that is acceleration of the system, equal to 0. Taking the x dash outside as a common factor, we get kx plus mx double dash equal to 0. Now the quantity x dash cannot be 0 because x dash is 0 only at extreme position, but this expression is a general expression for any time instant t, not just for the extreme position. So hence the quantity inside the bracket should be 0. So we get mx double dash plus kx equal to 0. So hence you can see here that we have got a same expression that what we got from the force balance study. So same equation of motion for the free vibration. The solution for that is omega is equal to k by m, and then a cos omega t plus b sin omega t is the solution. And you can solve it pretty much same way. But the thing what I wanted to highlight here is that you can get the same equation of motion by method of conservation of energy, that the total energy remains constant and derivative of total energy is equal to 0, and you can get the pretty much same equation without doing the force balance. This method will come handy in some special problems where it is just too difficult to do a force balance analysis. So there you can quickly get the equation of motion by using the conservation of energy. And once you get the motion for conservation of energy, you put it in a general format of second order homogeneous differential equation, and from that you can get the natural frequency of the system. So this method comes very handy in quickly determining the equation of the motion and the natural frequency of the system. Now next we will take up some numerical example on the topic of free vibrations, and then we will further go on to the damped and the forced oscillations.